Good morning, students. Today we have lecture number 8 on fluids. Lecture number 8 on fluids for first year. Lecture number 8 on fluids for first year. Okay. So in the previous classes, we have studied about the viscosity. In the previous classes, we have studied about the viscosity, and today also we will continue with viscosity. So now next concepts. Stokes law. Next concept, Stokes law. Okay. Before explaining Stokes law, I will tell something. Okay. When a body moves through a viscous fluid, when a body moves through a viscous fluid, the fluid which is in contact with the body will also move with the body. When a fluid moves through a viscous fluid, the molecules of the fluid which are in contact or which are nearby the body will also move along with the body, will also move with the velocity of the body. Whereas the molecules or the particles of the fluid which are far away from the body will remain at rest. Here, for example, a big lake is there. Okay, a big lake is there. There is a liquid. Okay. Okay. So now a spherical body is dropped in this water. When the spherical body, that is iron sphere, is dropped in the water, so it will fall. As it falls, the molecules of the liquid which are near the sphere will also move. The molecules of the liquid which are near the sphere will also move, whereas the molecules of the water which are far away from the sphere will remain at rest. As a result, a relative velocity is created, a relative motion is created between the liquids layer, and this results in the viscous force. As a result, the viscous force comes into action. The viscous force opposes the motion of the sphere. The viscous force opposes the motion of the sphere, and the magnitude of the viscous force depends upon the magnitude of the viscous force depends upon the shape and size of the sphere, the shape and size of the body, as well as on the viscosity of the liquid. The magnitude of the viscous force depends upon the shape and size of the body, falling body, as well as on the viscosity of the liquid. So here once again I will tell, when a body falls through a viscous liquid, the liquid molecules or the liquid which are very near to the body will moves with the velocity of the body, whereas the liquid molecules or the molecules of the fluid which are far away from the body will remain at rest. So this creates a relative velocity, and whenever there is a relative velocity there will be a viscosity. Thus viscosity comes into action, and the viscous force opposes the motion of the sphere. The viscous force opposes the motion of the body, and the magnitude of the viscous force, depends upon the shape and size of the body. The magnitude of the viscous force depends upon the shape and size of the body, and also depends upon the viscosity of the liquid. And this was studied by the Stokes. It was studied by the Stokes, and Stokes found that when a sphere of radius r is falling through a viscous medium, when a sphere of radius r falling through a viscous liquid and attaining a constant terminal velocity, attained a constant terminal velocity, then the viscous force acting on the sphere is given by F is equal to 6 pi eta RV. This is called Stokes law. According to Stokes law, here Stokes law means this much only: when a sphere of radius r, moves in a viscous liquid of coefficient of viscosity eta, when a sphere of radius r moves through a viscous liquid of coefficient of viscosity eta, the viscous force acting on the sphere is given by F is equal to 6 pi eta RV. Understood? Okay, once again I will tell what is Stokes law. Stokes law means this much only we have to write the definition of Stokes law. When a sphere of radius r moves through a viscous liquid with constant velocity v. When a sphere of radius r moves through a viscous liquid with constant velocity v and the viscosity, the coefficient of viscosity of the liquid is eta, then the viscous force acting on the sphere is given by F is equal to 6 pi eta RV. So this is called Stokes law. Understood? So define Stokes law or state Stokes law means this like this only you have to write. Understood? Okay, once again I will repeat. When a sphere of radius r moves with a constant velocity v in a viscous fluid, when a sphere of radius r moves with a constant velocity v in a liquid or fluid of coefficient of viscosity eta, then the viscous force or the dragging force acting on the sphere is given by F is equal to 6 pi eta RV. Understood? So this is called Stokes law. Understood my explanation once again. When a sphere of radius r moves with a constant velocity v in a viscous medium, in a viscous fluid of coefficient of viscosity eta, then the viscous force, that is the viscous dragging force acting on the sphere is given by F is equal to 6 pi eta RV. And the derivation of this Stokes law is not there. If you want, you can derive it by dimensional analysis. By using the dimensional analysis you can do on your own. Okay. Okay. Next expression for terminal velocity. Now expression for terminal velocity. Now we will derive an expression for terminal velocity. First understand what is terminal velocity. Okay. First I will tell once again from the beginning. Okay. So there is a liquid. There is a liquid of density sigma. There is a liquid of density sigma. When a sphere falls through a liquid, when a metallic sphere falls through a liquid, initially the sphere will move with acceleration. Initially the sphere will move with acceleration. That is, initially it will have a acceleration. After traveling a certain distance, the acceleration of the sphere becomes 0. When a sphere falls through a viscous liquid, after traveling a certain distance, the acceleration of the sphere becomes 0. Then sphere moves with a constant velocity. After that sphere moves with a constant velocity called as terminal velocity. Then sphere moves with a constant velocity called as terminal velocity. Once again I will explain. When a sphere falls in a fluid or liquid, when a sphere falls in a liquid or fluid, the sphere moves with a acceleration. Initially the sphere moves with a acceleration. After traveling a certain distance, the acceleration of the sphere becomes 0 because of the viscous force acting in the opposite direction. Because viscous force will act as a retarding force acting on the sphere in the opposite direction. As a result, the acceleration of the sphere becomes 0. Then the sphere will move with a constant velocity, and that constant velocity we called as terminal velocity. Understood? Now the definition. The maximum velocity with which the maximum velocity attained by a body, the maximum velocity attained by a body while moving through a viscous fluid. The maximum velocity attained by a body while moving through a viscous fluid is called as terminal velocity. Definition for terminal velocity. I am telling expression. Definition for terminal velocity. The maximum velocity attained by a body. The maximum velocity attained by a body. The maximum constant velocity. The maximum constant velocity attained by a body while moving through a viscous fluid. The maximum constant velocity attained by a body while moving through a viscous fluid is called as terminal velocity. Understood? Okay. So now derive an expression for terminal velocity. Consider a solid body. Consider a solid body or metallic sphere, like metallic sphere, a solid body of density rho and radius r. Consider a metal sphere or solid sphere of density rho. Rho is the density of the metal of the sphere and r is the radius of the sphere. Okay. Consider a sphere of density rho and radius r. Consider a sphere of density rho and radius r falling through a viscous liquid, of coefficient of viscosity eta. Falling through a viscous liquid of coefficient of viscosity eta and density sigma. Okay. This is liquid and this is sphere traveling with okay. This is sphere. Okay. So consider a sphere. Consider a sphere of density rho and radius r. Consider, I am deriving terminal velocity for expression for terminal velocity. Consider a sphere of density rho having radius r, moving in a fluid, moving in a liquid of density sigma, and coefficient of viscosity eta with a constant velocity v. Consider a sphere of density rho and radius r moving in a liquid of density sigma and coefficient of viscosity eta with a constant velocity v. Then the different forces acting on the sphere, are as follows. The different forces acting on the sphere are as follows. First one, the weight of the sphere. The weight of the sphere, that is W is equal to mg. The weight of the sphere, here I will write once again the diagram of the sphere. So acting downward, the weight of the sphere W is equal to mg, acting downward. That is W is equal to m. M is the mass of the sphere. Mass of the sphere can be done as density of the sphere into volume of sphere into acceleration due to gravity. So therefore W is equal to, that is W is nothing but weight of the sphere, and density of the sphere we have taken it as rho, and volume of the sphere will be 4 by 3 pi r cube, because radius of the sphere we have taken it as r and volume of a sphere is 4 by 3 pi r cube into acceleration due to gravity. Understood? So this is equation number 1. This is the weight of the sphere acting downward. And next B, the upthrust, that is the upward force acting on the sphere, due to the buoyant force, or the buoyant force acting on the sphere in upward direction. The upthrust or buoyant force is equal to the weight of the liquid displaced. That will be equal to the weight of liquid displaced. So now the weight of the liquid displaced can be done as, so that is mass into acceleration due to gravity. Mass of the liquid displaced into acceleration due to gravity. And mass of the liquid displaced can be done as density into volume of the liquid displaced. Density of liquid into volume of liquid displaced. Into acceleration due to gravity. So therefore upthrust, that is I will write it as T. So therefore upthrust T is equal to the density of the liquid Density of the liquid is sigma. Density of the liquid is sigma. And the volume of liquid displaced. The volume of liquid displaced will be same as the volume of the sphere, because the sphere is completely immersed in the liquid. When the sphere is completely immersed in the liquid, the volume of the liquid displaced will be same as the volume of the sphere, that we have studied in the Archimedes principle. So therefore, volume of the liquid displaced is same as volume of the sphere. So that is 4 by 3 pi r cube. So sigma is the density of the liquid. So into volume of the liquid displaced 4 by 3 pi r cube into g, that is acceleration due to gravity, and this one acts in the upward direction. It acts in the upward direction, and this one acts in the downward direction. Call this as equation number 2. And the third one, the viscous force. The viscous force acting on the sphere. The viscous force acting on the sphere in upward direction. T is in upward direction, and the viscous force acting on the sphere in upward direction, and it is given by 6 pi eta Rv according to the Stokes law. According to the Stokes law, the viscous force acting on the sphere, in a direction opposite to the direction of motion of the sphere. The direction of motion of the sphere is downward, so viscous force is acting upward, so F is equal to 6 pi eta Rv. So these all are the forces acting on the sphere. Here, when a sphere of density rho and radius r moves through a liquid of density sigma and coefficient of viscosity eta with a velocity v, then the different forces acting on the sphere are as follows. The weight of the sphere that will be acting in the downward direction, and the upthrust, that is due to the buoyant force. The upthrust or the buoyant force acting on the sphere in a upward direction, that is given by equation number 2. And the viscous force, that is viscous drag acting on the sphere in a direction opposite to the direction of motion of the sphere. So that is, and it is given by F is equal to 6 pi eta Rv, and it will be in a upward direction. Understood? And now the sphere moves with a constant velocity. Because terminal velocity is a constant velocity. So the net force acting on the sphere will be 0. I will write here only. The net force acting on the sphere will be 0. When a sphere moves with terminal velocity, terminal velocity is a constant velocity, which is constant. When a sphere moves with terminal velocity, the net force acting on a sphere is 0. The net force acting on sphere is 0, because when the net force acting on a body is 0, then only the velocity will remain constant. That is, we have studied in the laws of motion. In the laws of motion we have studied a body will have acceleration only when there is a net force acting on the body. So here acceleration is 0, that means the velocity is constant, and velocity is constant only when the net force acting on the body is 0. That is possible. That is, you can write, I will write directly, that is the total downward force is equal to total upward force. Then the net force acting on the body will become 0. That is, W is equal to F plus T. Or you can write F is equal to W minus T. And now substitute the values. And F is 6 pi eta Rv is equal to W. W is here. So it is 4 by 3 pi r cube. 4 by 3 pi r cube into rho into G. That is W minus T. That is buoyant force acting on the sphere. That is, also you can write 4 by 3 pi r cube. 4 by 3 pi r cube sigma into G. So now simplify this equation. That is, so take the commons. 4 by 3 pi r cube and G is taken common. 4 by 3 pi r cube into G is taken common. then rho minus sigma. Then here 6 pi eta r v. So what are the things cancel? Pi will cancel. So therefore v is equal to write one more steps. No problem, write one more steps. So v is equal to, it is 4 by 3 pi r cube into g rho minus sigma and divided by 6 pi eta r, 6 pi eta r. So now pi cancel and that one r cancel. So v is equal to 4 divided by 18. 4 divided by 18. 3 into 6, 18. 18 into r square. R square and g remains. R square g divided by eta into rho minus sigma. Understood? Correct? So r square will cancel and eta will remain over there and g will remain. So this is the expression for terminal velocity, and 4 by 18 can be done as 2 by 9 r square into g into rho minus sigma divided by eta. So this is the expression for terminal velocity. This is the expression for terminal velocity. Remember that. What is the terminal velocity? Once again I will tell the definition. What is the terminal velocity? The maximum velocity attained by a body. The maximum velocity attained by a body while moving through a fluid. The maximum constant velocity. The maximum constant velocity attained by a body while moving through a viscous liquid is called as terminal velocity. So therefore, and the expression for terminal velocity is given by v is equal to 2 by 9 into r square g into rho minus sigma. Rho minus sigma divided by eta. Understood? Okay, this is a derivation. Okay, in sometimes in the exam only they will ask like this. Write the expression for terminal velocity and explain the terms. Write the expression for terminal velocity and explain the terms for 2 marks or 3 marks. So you have to directly write the formula. Don't derive the formula, just write the formula and explain the terms. What is v? V is the terminal velocity of the sphere, r is the radius of the sphere, and g is acceleration due to gravity, and rho is the density of the material of the sphere, and sigma is the density of the liquid, and eta is the coefficient of viscosity of the liquid. Coefficient of viscosity of the liquid. Understood? Okay. So like this you have to explain the terms. Understood? So derivation, if they ask, write all the things. Okay. So now if they ask what are the factors on which terminal velocity of a sphere depends? What are the factors on which terminal velocity of a sphere moving through a viscous liquid depends? So if they ask a question like this, then what will be the answer? The terminal velocity of a sphere moving through a viscous liquid depends on the square of the radius, depends upon the acceleration due to gravity, depends upon the density of the sphere, and depends upon the density of the viscous medium, and also depends upon the coefficient of viscosity. So it is the factors on which terminal velocity depends. The terminal velocity of a body depends upon the radius of the body, acceleration due to gravity, density of the body, density of the liquid, and as well as coefficient of viscosity of the liquid. So these all are the factors on which terminal velocity of a body depends. Okay. Understood? Okay. Next point. Let us understand some points, CET points. We observe that the terminal velocity of a body is directly proportional to the square of the radius. The terminal velocity, CET points, just for our understanding I am telling. The terminal velocity of a body is directly proportional to the square of the radius. If radius is made n times, then terminal velocity becomes n square times. If the radius is increased by n folds, if the radius is increased or decreased by n folds, then terminal velocity will also increases or decreases by n square times. Understood? So remaining all the other factors constant. Understood? Okay, next. So now second point, if a body, so that is if density of the body is greater than the density of the liquid. If the density of the body is greater than the density of the liquid, then the body moves downward. You know that is we have studied in the law of flotation. Law of flotation I have told already. We have completed in the previous lectures only. Law of flotation. In that we have studied that a body will sinks in a liquid when the density of the body is greater than the density of the liquid. So the density of the material of the body is greater than the density of the liquid, then the body moves downward. The terminal velocity is positive. If density of the body is greater than the density of the liquid, then terminal velocity is positive and the body moves downward, with a terminal velocity v. The body moves downward with a terminal velocity v. Understood? Okay. So if density of the body or density of the sphere is less than, example for this one, I will give example for this one. Example for this one is the motion of raindrop in the atmosphere. The motion of raindrop in the atmosphere. Understand properly. Raindrop means what will be there inside that drop? Raindrop means what will be there inside the drop? So raindrop is almost spherical in shape. Almost spherical. What will be there inside the drop? Inside the drop there will be water. And outside the raindrop what will be there? That is atmosphere. It is gas, air medium. Air medium will be there. And density of the sphere, it is density of the raindrop is greater than the density of the fluid surrounding it. Hence, the raindrop will move downward in the atmosphere. The raindrop moves downward in the atmosphere with the terminal velocity. Understood? Got the idea? And terminal velocity is positive. Got the idea? This is example. Density of the sphere is greater than the density of the liquid, then the terminal velocity will be positive. That is, this rho is greater than sigma, then this entire thing become positive, then this terminal velocity become positive, then the object moves or the sphere moves downward. Okay. Second point, if density of the sphere is less than the density of the surrounding medium or liquid medium, fluid. If the density of the sphere is less than the density of the fluid, then this is smaller number and this is bigger number. Smaller number minus bigger number, it will be a negative. Negative into all these things will becomes negative. So the terminal velocity will be negative. The terminal velocity is negative. Then the sphere moves upward. Then the sphere moves upward in the fluids. The sphere moves upward in the fluid. The sphere will move upward in the fluid. Give an example for this one. Think about example for this one. Who will think? Will think? Think an example for this one. Just now I told an example of raindrop in the atmosphere, right? So now the density of the sphere is less than the density of the surrounding medium. That is density of the fluid. Then the terminal velocity will be negative, and think about example, and the sphere will move upward. Okay. Now I will tell the example. The air bubble inside the water. The air bubble inside the water. The water is there. So in this water there is a air bubble. Which bubble? Air bubble. Air bubble means what will be there inside the bubble? Air bubble means what will be there inside the bubble? Inside the bubble there will be air. That is, the sphere is made up of air and the surrounding medium is water. Density of the air, density of the sphere is less than the density of the water. This is water and this is air bubble. So then the terminal velocity will be negative. That means the air bubble moves upward or downward? The air bubble moves upward in the water. Understood? Why air bubble moves upward? The air bubble moves upward because density of the air is less than the density of the water. Hence, the air bubble moves upward and the terminal velocity for that air bubble will be negative. Understood? Okay. Further, one more concept I will tell. The size of the air bubble, as it moves upward, the size of the air bubble increases or decreases? Think about it. Let us consider that the air bubble is moving through a larger distance of liquid. larger distance of water. So when the air bubble is at the bottom, what about the size of the air bubble? And when air bubble reaches the top surface of the liquid, top surface of the water, then what about the size of the air bubble? What happens to size of the air bubble? Whether the size of the air bubble increases or decreases, think about it. I will tell about that in the numerical. Okay, understood? So these things you have to understand. Understood? So terminal velocity will be positive for a raindrop, and for a air bubble the terminal velocity will be negative. Okay. So now next, the variation of terminal velocity. A graph is drawn for variation of terminal velocity with time or distance. With time or distance. When a graph is drawn for variation of terminal velocity with time or distance, the graph obtained will be like this. The graph obtained will be like this, with the time or distance. When a graph is drawn for the variation of terminal velocity, with time or distance, then the graph will be like this. Okay. Okay. Did you understood all these things? So this is about terminal velocity, and this concept are important. And remember that about this terminal velocity, many times in the CET exam they will ask the question. CET exam, and as well as numericals, there will be numericals on this concept. And here one more concept. So this terminal velocity expression can also be made into expression for coefficient of viscosity. That is, eta is equal to, you can write eta is equal to 2 by 9 into r square g into rho minus sigma divided by V. So now by using this formula you can find the coefficient of viscosity of liquid. You can find the coefficient of viscosity of liquid. You can determine the coefficient of viscosity of liquid by doing a simple experiment. By doing a simple experiment, you can determine the coefficient of viscosity of liquid. Understood? So take a metal spheres and move them through the aisle medium of large glass tube. Take a large glass tube filled with aisle or water whose density is known, and take metal sphere and the density of that metal sphere is known and radius of that metal sphere is also known, and then the velocity, measure the velocity of that sphere while moving through that aisle. Then you can measure the coefficient of viscosity. So velocity, how velocity can be measured? Measure the distance of the aisle medium. Take a stop clock. As you drop the sphere, start the clock. As it reaches the bottom, stop the clock. And the time taken to measure, to travel this distance, so that the distance travelled divided by time will be the velocity. So let us take that as the constant velocity, that is terminal velocity. Repeat the experiment many times, so you will get roughly, will get nearby correct answer. So the coefficient of viscosity of a liquid can be determined by using this formula, by knowing the radius of the sphere, density of the liquid, and terminal velocity. The coefficient of viscosity of a liquid can be determined practically. Understood? Okay. So this is about terminal velocity. So next concept we will study. Now we shall study about the next concept, Poiseuille's equation. Poiseuille's equation. Poiseuille's equation. Okay. Now let us study about the Poiseuille's equation. Next concept, Poiseuille's equation. Poiseuille have studied the streamline flow of liquid through a capillary tube. Poiseuille studied about the streamline flow of liquid through a capillary tube. What is a capillary tube? First I will tell what is a capillary tube. Capillary tube. A glass tube of very fine bore. A glass tube of very fine bore is called a capillary tube. A glass tube of very fine bore. This is a glass tube. Glass tube, and the bore, that is the hole, is very small. It is, I will draw the diagram. I will just draw the diagram for your understanding. A glass tube of very fine bore is called as capillary tube. So this is a capillary tube. This is a glass tube. Okay. So through this small tube, the liquid will comes out. What is a capillary tube? A glass tube of very fine bore is called a capillary tube. Like this, there will be a capillary tube. In the lab, you will have a capillary tube. You will see a long tube having very thin small hole will be there. Through that hole, the liquid will comes out. The steady flow of the liquid through a capillary tube is studied. The PATIL studied the steady flow of a liquid through a capillary tube, and it is found that the liquid will flows from higher pressure region to lower pressure region. That is, we already know. When the liquid is maintained in a when the capillary tube is maintained at a horizontal level and a pressure difference P is maintained. When a pressure difference P is maintained between the two ends of a capillary tube of length L and radius R. When a pressure difference of P is maintained between the two ends of a capillary tube of radius R and length L, the volume of liquid coming out of the capillary tube per second. Volume of liquid flowing out or coming out per second is V. Okay, see here. The PATIL studied the streamline flow, that is steady flow of liquid through a capillary tube. When a pressure difference of P is maintained between the two ends of a capillary tube of length L and radius R, the volume of liquid coming out per second, the volume of liquid coming out per second from a capillary tube is V, and it is found that the volume of liquid coming out per second from a capillary tube is directly proportional to the pressure difference between the two ends of the capillary tube. The volume of liquid coming out per second from a capillary tube is directly proportional to the pressure difference between the two ends of the tube. The volume of liquid coming out per second, from a capillary tube is directly proportional to the fourth power of the radius of the capillary tube. The volume of liquid coming out per second from a capillary tube is directly proportional to the fourth power of the radius of the capillary tube. The volume of liquid coming out per second from a capillary tube is inversely proportional to the coefficient of viscosity of liquid. The volume of liquid coming out per second from a capillary tube is inversely proportional to the coefficient of viscosity of liquid, and it is found that the volume of liquid coming out per second from a capillary tube is inversely proportional to the length of the capillary tube. So these all are the inventions made, these all are the findings that has been made by the PATIL. PATIL has discovered all these things. Then he combined all these formulas. That is V, that is volume of liquid coming out per second from a capillary tube, is proportional to P r raised to 4 divided by eta L. P r raised to 4 divided by eta L, where P is the pressure difference between the two ends of the capillary tube, R is the radius of this fine bore, radius of the capillary tube, and eta is the coefficient of viscosity of the liquid, and L is the length of the capillary tube. And now V is equal to, remove this directly proportional, write a constant, and that constant is K, P r raised to 4 divided by eta L. So this is where K is a proportionality constant, and value of K is found to be, K is a proportionality constant, constant and value of k is found to be pi by 8. So therefore V is equal to you can write pi p r raised to 4 divided by 8 eta L. So this is called as Poiseuille's equation. This equation is called as Poiseuille's equation. Understood? So Poiseuille's equation, what is V? V is the volume of liquid coming out per second, volume of liquid flowing per second from a capillary tube, and P is the pressure difference between the two ends of the capillary tube, R is the radius of the fine bore of the capillary tube, and eta is the coefficient of viscosity of the liquid coming out, and L is the length of the capillary tube. Understood? And this formula can also be written like this. This formula can also be written like V is equal to P divided by R. V is equal to P divided by R. That is volume of liquid coming out per second is equal to pressure divided by R, where R is equal to, so that formula will becomes 8 eta L divided by pi R raised to 4. 8 eta L divided by pi R raised to 4. This is the expression for R, and R is called as liquid resistance. R is called as liquid resistance. R is called as liquid resistance. Understood? So this is the expression for Poiseuille's equation. Understand this? The same formula can be done as V is equal to P divided by R. V is the volume of the liquid flowing per unit time. P is the pressure difference, and R is the resistance, that is liquid resistance, and capital R is liquid resistance is given by 8 eta L divided by pi R raised to 4. Understood? So from this further you can write, further you can understand some more concept called when there are two tubes connected in a series, what happens? When two tubes connected in series like this, when there are two tubes, so they are connected in a series, then what will be the effective liquid resistance? You can find, do it on your own, you will get some book, read from some book, it's all CT concepts. So then R effective is given by R1 plus R2 when two tubes are connected in parallel. When two tubes are connected in parallel, then R effective is given by R1 into R2 divided by R1 plus R2. So these all are the formula you study for CT. These all are for CT. When two tubes are used in a series connection and parallel connection, then what happens to the liquid resistance? Understood? So this is Poiseuille's equation. So this is all about theory part for viscosity. Understood? So this completes the viscosity. So next, in the next class we will study about the surface tension. In the next video we will study about the surface tension.